Hello everyone. Today we are going to talk about inverse trigonometric functions and solve some problems in that field. Now recall that every function has an inverse, and that inverse is only a function if and only if the original function is 1 to 1. Now let us take a look at the graph of y is equal to the sine of x. Now, in order for a function to be 1 to 1, it must pass the horizontal line test. Clearly, this function fails the horizontal line test because it passes the horizontal line passes the function at more than 1 point. But if we restrict the domain of the function to negative pi over 2 less than or equal to x less than or equal to pi over 2, then the function passes the horizontal line test, which means we can take an inverse of this function. Now remember that taking an inverse of the function is same as reflecting it across the line y is equal to x. And when we perform the reflection, we get the graph of y is equal to the inverse sine of x, which is in purple. Now, let us take a look at this graph. The domain of the function, which is all possible x values, starts at -1 and ends at 1. That means the domain of the function is from -1 to 1. And the range of the function is all possible y values, and that is negative pi over 2 to pi over 2. Let us take another example. Here is the graph of y is equal to cos of x, highlighted in blue. Now clearly, this function fails the horizontal line test, but when we restrict ourselves to the domain 0 less than or equal to x less than or equal to pi, we get this function that passes the horizontal line test, which means that we can take an inverse. Now, always remember that the cos inverse function is only defined for this interval of cos x, 0 less than or equal to x less than or equal to pi. Now, when I reflect this across the line y is equal to x, we get our inverse function highlighted in green over here. Now let us see the domain and range of the function. Now this function starts off at a value at an x value of -1 and goes to an x value of 1. That means the domain of cos inverse x is -1 less than or equal to x less than or equal to 1. Notice that that's the same as the sine inverse function. However, the range is different. This starts off at pi up here and goes to 0. So the range of this function is 0 less than or equal to y less than or equal to pi. Let's recap the basic facts of the 6 inverse trigonometric functions, starting with sine inverse x. In order for sine inverse x to be defined, we need to restrict the domain of y is equal to sine x to in between negative pi by 2 to pi by 2, which gives us this red graph shown here. Now when I reflect this across the line y is equal to x, we get the graph of the inverse sine of x shown in green. Now, observing this graph, we can conclude that the domain of the graph is from -1 to 1, and the range of the graph is from negative pi by 2 to pi by 2. Now we know that f of f inverse x is equal to x. We also know that y is equal to sine inverse x is the graph. Now taking sine on both the sides, we get sine y is equal to sine of sine inverse x. And now using the previous fact and using it over here, we get sine of y is equal to x. So which that is going to give us a very, very important conclusion that if y is equal to sine inverse x, then sine y will be equal to x. Let us now look at cos inverse x. In order to define cos inverse x, we need to restrict the domain of cos x to between 0 and pi. And then when we reflect it across the line y equal to x, we get this blue graph, which is the graph of y is equal to cos inverse x. Now, we know that the domain is between -1 and 1, and the range is in between 0 and pi. Because we know this is true, we can use applying the same principles as before. When given an equation y is equal to cos inverse x, we can conclude that cos y is equal to x. Similarly, let's look at tan inverse x. In order for us to take the inverse, we need to restrict the domain of tan x to between -pi/2 and pi/2. And when we take the reflection across the line y is equal to x, we get the blue graph, which is the graph of y is equal to tan inverse x. As you can see, this graph is defined for all real x, and its range is from -pi/2 to pi/2. Similarly, we can use the same principles as before. If y is equal to tan inverse x, we can show that tan of y is equal to x. Next up, cot inverse x. This time I'm going to restrict the domain of cot x to between 0 and pi. And this time when I take a reflection across the line y equal to x, we get the green graph, which is the graph of y is equal to cot inverse x. The domain of this is all real values of x, and the range is from 0 to pi. Now, given that y is equal to cot x, cot inverse x, we get that cot y is equal to x. Now let's look at the graph of y is equal to cosec inverse x. Notice that the graph of y equal to cosec x is not defined at x is equal to 0. But still, we will restrict it between -pi/2 to pi/2. When we reflect this across the line y equal to x, we get the graph of y is equal to cosec inverse x highlighted in blue. Now, the domain of this function is all real x less than -1 and all real x bigger than 1. And the range of the function is from -pi/2 to pi/2, but notice that the function is not defined at 0. Now, given that y is equal to cosec inverse x, we can derive that cosec y will be x. Let's now look at the last inverse trigonometric function, that is sec inverse x. Now the graph of y is equal to sec inverse x is shown in red, and notice that it's not defined at pi/2. Still, we're going to restrict it to between 0 and pi, and when we take the reflection across the line y equal to x, we get the blue graph, which is the graph of y is equal to sec inverse x. Now, the domain of this function is all real x less than -1 and all real x bigger than 1. And the range of this function is from 0 to pi, but notice that it's not defined at pi/2. Now, given that y is equal to sec inverse x, we can prove that sec y is equal to x.